Hey there. Let's work a few homework problems. Starting back in 5.1, we've actually only worked one problem out of that in the lectures here. So let's work some others. Starting with number 6, get over here where you can see me a little bit better. 6a is we're talking about a relation f defined on R, defined by x, f, y if x minus the floor of x equals y minus the floor of y. So let's talk about this. There's absolutely nothing there that I can't plug in. So domain is all reals. There's nothing restricting y either. So again, all the reals. Oh, that's not true, is it? Because every time here we're going to get something between. Well, I thought that through. The least this could be is 0, right? If x is an integer and you subtract the floor, then you get 0. Or the y. I guess I'd technically be looking at the y, but they're the same, right? And then the biggest this could possibly be is, up to just shy of 1, right? Because if it's 8.999999998, then, or just 9 and it stops, then all that 8 business goes away and it's the 0.9. So actually, this is glad I caught this. 0 to 1 is where that's gonna that'll be the range of this. Let's see. No, it's not. I was right. I'm completely. Ugh. It's all the things that can go here, right? All the things that can be related to, which is R. Okay. I'm losing my mind. I'm sorry. I'm thinking about the criteria here, and that's not at all what we need to do. It's mapping x into y. X can be any real number. Y can be any real number. I was right to start with. I don't know why I was thinking about that. Okay. So anyway, off to a bad start, but we'll do better. Question is it reflexive? Can x be related to x? Well, of course it can. In fact, that would definitely be equal if you had an x over here replacing a y, right? So yes, that is reflexive. Symmetric? Well, because I can take the x and y and flop them over like that, yeah. Right, symmetric means if x is related to y, then y is related to x. Of course it is. Transitive, well, sure, if x is related to y and y is related to z, that means that x is equal to this, which is equal to that. So, sure. Antisymmetric? No, it's not going to be antisymmetric because it's symmetric with everything in the world that's in there, right? And you just need to come up with one example. One is related to 2, right? Because 1 minus the floor of 1 is 0, and 2 minus the floor of 2 is 0. And 2 is related to 1 for the same reasons, right? But 2 is not equal to 1. So there's a counterexample. So no. Okay. Because it's reflexive, symmetric, transitive. Now in 5.1 we hadn't talked about this yet, but we talk about it in 5.2 about equivalence classes. This is an equivalence relation because it's reflexive, symmetric, and transitive. If you think about what it does, 0, 1, 2, here's my number line for the real numbers. It takes everything that's a certain distance to the right of a integer and relates it to everything else that's a certain distance. So all those things like this would be related, and that's the equivalence class. So that's the equivalence classes, and we talked about in that section how equivalence relations actually partition the set, in this case the real numbers, into subsets that take the union. Partition means you don't repeat stuff, and then disjoint sets that give us whose union is the entire set. So that's what the equivalence classes would look like there. Okay, I'm sorry for that I don't know what I was thinking there. I started out right and then I doubted myself. Never do that. Okay. 6b, relation Q defined on R square by a point is related to another point if this x squared plus y squared, the x and y coordinates, the first point equals the z squared plus w squared, that's the first and second coordinates, each squared for the second point, which is basically the square of their distance from 0, right? So any of the points in R2 work with this. Any of the points in R2 work in the second one. Is it reflexive? Well, sure. If xy, we say, is xy related to xy? Well, sure it is. This sum would equal x, replace the z with x and the w with y. Sure. Is it symmetric? Well, again, if you take these things and say this happens and then turn it over, then the other thing happens, right? So, yes. Is it transitive? Well, sure. If this is related to this, and these things are equal, and then this is related to something else, so it's equal to another thing, then this is equal to that. Sure. Is it anti-symmetric? Well, no. There's all kinds of ways to. You just need a couple things that, for example, the point 1, 2 is related to the point 2, 1 because the sum of their squares would be the same, right? And I can switch the order because the sum of their squares is the same. But those are not equal points. Okay, so it's not anti-symmetric. So again, this is an equivalence relation, right? It's reflexive, symmetric, transitive. And what it does, it breaks, if you look at things that are in the same equivalence classes, well, anything the same distance from 0, those circles of different radii, right? And that's a way of partitioning R2. Okay? All right, so that is 6b. 6c says, okay, we've got this relation V defined on R2 by this point V, that point, if and only if x is less than z. Okay. If and only if x is, this point related to that point, if and only if x is less than z, so the first coordinate less than that coordinate, first coordinate, or the first coordinates are equal and the second coordinate is less than or equal to that second coordinate. Okay. There's nothing prohibiting any of R2 in being in either one of these spots. Right? So, oops, R2. Okay, so let's talk now about reflexive. Is xy related to xy? Well, sure. X would not be less than x, but x would equal x, and y would be less than or equal to y. Okay, see what I'm talking about here? If you put x, y in here again, x is not strictly less than x, but it is equal to x, and y is less than or equal to y. So it falls in this part over here. Symmetric. I don't think so. Let's come up with a counterexample. I think probably, yeah, all I got to do is just make sure that my first coordinates are not the same, right? So let's see, maybe 1, 2. Since 1, 2 is related to 2, 1, that's all it takes. But 2, 1 is not going to be related to 1, 2. Right? First of all, 2 is not less than z, and then it's not equal. 2 is not equal to z, or x is not equal to z. 2 is greater than 1, so that blows it up. Okay? Transitive. Now this one you might need to think about a little bit. Okay, let's think about what this means. If xy is related to zw, then x is less than z, or x is equal to z, and y is less than w. Okay. Likewise, if zw is related to, let's get something else, ab, then, I'm sorry, z is strictly less than a, or z equals a, and w is less than or equal to b. So if we're saying and, both these things happen, right? I've got this or, that or. I've actually got 4 things I've got to check on here, right? I could have the case where x is less than z holds. You know, one of the two has to hold in each of these cases. So this happens and z is less than a. That's the first case that I'm going to look at. Well, in that case, x would be less than a, and that would be enough to say that this is related to that. So, and so x, y would be related to AB. Or maybe this happens and that happens. So x is less than z, and z equal a, and w is less than or equal to b. Well, in that case, if z is equal to a, then x is less than a, because x is less than z, and that's all I needed. That means then that xy is related to ab. Or maybe this one happens. X is equal to z, and y is less than or equal to w, and z equals a. Now I'm going back over here. Well, that means that x is equal to a, right? Oops, sorry. Oh, no, I thought, I was like, that doesn't make sense. But I'm over here. It's not equal, it's less than. My bad. All right, so z is x is equal to z, which is less than a. So x is less than a. There we go. So that takes care of that. X, y is related to AB. And then the fourth case is where x equals z and y is less than or equal to w, and z is equal to a and w is less than or equal to b. Well, when that happens, x is equal to z, which is equal to a, so x is equal to a, and y is less than w, which is less than b, so y less than or equal to b. And that's all it takes. So xy is related to AB. So that does mean that it is transitive. Okay. And then asymmetric. Again, I think we would need to think about this just a little bit. What we ask is if two things are related in opposite ways. So I'll leave my answer here. Let's think. If xy is related to zw, then that means that x is strictly less than z, or x is equal to z, and y is less than or equal to w. Okay? And the second part is, okay, if zw is related to xy, then either z is strictly less than x or z equals x and w is less than or equal to y. Okay? So now we start looking at and I forgot to underline this one case. We start looking at these cases. Well, some of them are nonsense. X is less than z and z is less than x can't happen, right? X is less than z and z is equal to x. Well, that can't happen either. And same thing here. X is equal to z and this, and z is less than x. That can't happen because they're equal. So the only case, the only possible case is where x equals z and y is less than or equal to w, and z equals x and w is less than or equal to y. Well, then x and z are equal. And if y is less than or equal to w and w is less than or equal to y, then y equals w. Okay? Which means it's antisymmetric, right? That's what we had to show, is that if this happens, these 2 points are equal to each other. And sure enough, they are. So yes, it is antisymmetric. Okay? And that's 6C. And then 6D, we have relation K defined on R, saying that X is related to Y if and only if they're inversely proportional to each other, right? Y is 1 over X. Domain here, it's, we're doing things on R, but I cannot put a 0 in the denominator here, so R minus 0. And then also, Y can't be 0 because I got this 1 in the numerator, so again, R minus 0. Okay. All right. Reflexive is x related to x in all cases. Not even close. In fact, there's only a couple places where they are. I think 1 is related to 1 and -1 is related to a -1. But everything else I think blows up. In fact, the biggest blow up is the fact that I don't have 0 in either the domain or the range. This is not in K, and it has to be, so no. But an symmetry would work, because if you think about this also means that x is 1 over y, or if you prefer, yx is 1. So if I change out the x and y, it'll still work. Right? Transitive won't, though. This is kind of like a flip back and forth, right, between a number and its reciprocal. So, there's tons of examples, but we could say 2, oops, I don't want to do word pairs. 2 is related to 1/2, because their product is 1. And 1/2 is related to 2, but 2 is not the reciprocal of 2. Right? So, no. And then antisymmetric, for the same reasons, right? This is true, but they're not equal to each other. No. Since 2 is related to 1/2, and 1/2 is related to 2, but 2 is not equal to 1/2. Okay? So that's 6D. 7 says, all right, well, how many relations are on S? Well, if you think about how many things are in S how many relations are there on S? Well, anything on S is going to be a subset of the Cartesian product of the set with itself. And this actually has 3 times 3, 9 elements in it. Right? You can almost count them out. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay, so there they are. So how many relations are there? Well, each one of those things I just mentioned can either be in the relation or not. So the answer is 2 to the 9th power. 2 times 2 times 2 times 2, 9 times. And that's fundamental counting principle, which we'll get into a little tougher after our exam, or after we finish with our material here. Okay, the B part says how many relations are reflexive? Well, they must have certain ordered pairs, right? In this case, they've got to have 1, 1, 2, 2, and 3, 3. Okay. I don't know why it does that. That is so odd. So that leaves us with 6 things floating around, and each one of those has a choice of being in there or not. So 2 to the 6. I think this is 512, and I believe this is 64. There we go. So C says find all relations R on S such that it's reflexive, which means you're going to have these, and then you've got these additional 3 ordered pairs. So 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, and 2, 3. Union with the following things, and let me just number them. Right, we could leave it alone, right? Do nothing to it, so that's 1. So we're unioning. I didn't mean put the stem on the U there. The union. We could union with R1, which is just the empty set, or we could do all the single things left over. 1, 1, 1, 2, 1, 3. What's left over? 2, 1. Two 2's there, but 2, 3 is, and then 3, 1. Or 3, 2. Or we could do pairs of these, leaving 1 out, so we could leave out the 2, 1. R6, we could leave out that one. R7, we could leave out that one. Or I could just put them all in. The domain and range of each of these, well, if you just look at the base set without adding anything to it, we've got 1, 2, and 3 in the first coordinates, and 1, 2, and 3 in the second coordinates. So it's going to be domain is going to be 1, 2, and 3, or just S, and same thing for the range. So then they want us to make a table of all the things that could happen here. They're all reflexive. We built them that way. Okay. Transitive, let's see. I'm not so much worried about these as I am 1 to 2 and 2 to 3. 1 to 3 is good. 1 to 3 and 1 to 1. 1 to 3, 3. Yep, okay there. 2 is 3, 3 is. So I think we start out transitive. That's the first one. We add 2, 1. 2 goes to 1 and 1 goes to 3, so there. 1 goes to 2 and 2 goes to 1, right? So I think that works okay. If we put in 3, 1, without putting in the 2, 1, though, we've got problems, right? Because 2 goes to 3, 3 goes to 1, but 2 does not go to 1 unless we put that in there. So that's not transitive. And then fourth, 2 goes to, let's see. Yeah. 3 goes to 2, and no, that would work. 3 goes to 2, and yeah, I think that will work. Okay. And then let's see here. I think we can always kind of mess up by not putting all of them in here. Let's see. 2 goes to 3 and 3 goes to 1, but we don't have the 2, 1 in there, so that won't work. And then if we leave this one out, 3 goes to 1. Oh yeah, I'm sorry, I'm up here. 3 goes to 2 and 2 goes to 1, but 3 doesn't go to 1 if we leave that one out. And then this one, we leave out this one. So 3 goes to 1 and 1 goes to 2, but we don't have 3, 2 in there. But when you put them all in there, you'll get it. Okay. None of these are going to have symmetry, I don't think. Certainly not the way it is. And we can't put really enough things in there, I think. 2, 1 won't get it because 1, 3 is not in there. 1, 3 is, but 3, 1 isn't. And you put 3, 1 in, you don't have 1, 2. And you put in 3, 2, you don't have 3, 1. So every one of these has a counterpart over here. If you don't get them all in, these are all going to be no's as well. The only way you get them is if you put them all in. And then anti-symmetric, no, because we do have the reflexive things in here. Oh, I'm sorry, that's not what we need. Let's see. Actually, we are okay just at the onset. But the problem is, as soon as I put one of these things in here, it's got a counterpart, right? 2, 1 and 1, 2, 3, 1 and 1, 3, 3, 2 and 3, 2, 3. So that's going to tear them all up. Okay. So that is 7. And then the last problem we'll do before we stop here and take a little breather is problem 9 talked about how a relation R is irreflexive if it has none of its double coordinates, right? None of its AAs for every A in the set. So if we want to find an example of a relation that's not, that doesn't have this property, but it also isn't reflexive, then all you got to do, remember both those are for all A in the set, set type of conditions. So as long as you do part of the set one way and then part of the set leave it out. So let's say that maybe S is 1, 2. Okay. Then here's a relation that is not going to be reflexive, but it won't be irreflexive either. I'll just put in one of them, one of the doubles. Okay. And that would take care of it. Right? I've got 1, 1, but not 1, 2, so it's not reflexive. I'm sorry, 1, 1, but not 2, 2, so it's not reflexive. But I do have 1, 1, so it's not irreflexive. Okay? All right. And then B says list all the relations on this that are irreflexive. Well, clearly, if I got the empty set, I don't have any of my doubles. And then let's just go through and build ordered pairs that aren't doubles. I can have 1, 2. I could have 2, 1. I could have actually both of those. But what I can't have is 1, 1. I can't have 2, 2. Okay? Alright, so there's a little bit of our homework done. We'll pick up after problem 9 in the next one. And I hope these are helping you understand how to work these problems. I will see you next time.